So energy efficiency, that's sort of a big theme in this program is, looking at everything we do with technology, sustainable technology in the built environment. A lot of it revolves around energy efficiency and reducing our carbon footprint and our energy footprint, stuff like that. So in these learning objectives, and I did go ahead and post the quiz questions for today, and I posted the quiz as well, just as an aside. So we need to remember why buildings should be energy efficient. We want to understand how standards, codes, and certifications play a role in energy efficiency. And we want to list important features of a low energy building. And like I said, there's a lot of ways to do that. And the codes and the standards sort of give us repeatable method for doing that. So sort of an overview or a broad overview of why this stuff is important. So fossil energy is resource intensive. Every type of energy that we use requires some sort of infrastructure or some means of extraction, right? To get oil, we have to drill for it. To get natural gas, we have to frack for it. And there's a lot of stuff that goes into these processes, even renewable energies. You have solar and solar thermal and, wind and nuclear. All of this stuff requires some sort of energy input and materials to extract these energy resources. Solar panels are made from high energy intensity materials. The stuff the panels are made out of require high energy to process those materials and get them into the form that they need to be before they go into the panels. So that's something to think about when you guys that are studying appropriate tech and stuff like that. The easiest thing to do is to build an energy efficient building, and negate that need for excess energy production. You can put solar on all day long, but if your building is wasting energy, then you're wasting those materials and resources and energy that you create. So many countries are dramatically increasing energy consumption. China and India are, two of the most populated countries in the world, and China uses a lot of coal, but they're starting to use a lot of solar, and India uses a lot of coal. In these really densely populated sort of developing countries like India, there's a lot of energy scarcity. Not everybody has access to energy, and people use whatever they can, right? And a lot of countries are trying to raise their standard of living, and that takes energy to do that, and it's, we have a really high standard of living here in the U.S., and we've come up with all these ideas on energy efficiency and stuff like that, and we're looking at other countries and saying, you guys should do this, this, and this when you're trying to up your standard of living, when we went about it in the easiest and fastest way possible. So that's something to consider when we're looking at energy efficiency on a global scale. Everybody has the right to the same standard of living, and has the right to resources and stuff like that they need to be happy and healthy, but not everybody has access to that stuff. So and ultimately the issue is that when these energy resources become scarce, we go to war over them, right? We go to war over oil. Water is becoming more scarce with climate destabilization and stuff like that. And, that's one thing that you look at in a lot of your classes is the water intensity of things like farming and how much water goes into producing, a cow or a chicken or something like that. Some of that stuff is really water intensive. And fracking, they use a ton of water in fracking, and then it comes back out of the ground and they just dump it into pits. It's full of chemicals and stuff like that, evaporates into the air, and then, makes farm animals sick, yada, yada, yada. So a lot of the things that we use for energy, especially this, when we're making stuff for renewables, we're burning. When we process metals, we burn things to get a really high, because they require a lot of energy. So when we're burning things, it impacts the climate, right? The plot on the right shows some of these uses of fuel and the relation between carbon dioxide and the use and our fuel use. So, you know, carbon dioxide in the atmosphere is continuing to go up. You know, there's a direct correlation between increase in fuel use and the amount of carbon dioxide in the air. And we're at 400 parts per million right now, over 400 parts per million. And when CO2 dissolves into water, it creates carbonic acid. So the oceans are acidifying, and that affects life in the ocean. It affects the ocean's ability to absorb CO2. It affects a lot of things. It affects, you know, affects weather and like thermohaline current, I think, is something we talked about in one of the physics classes. But sort of some of those driving forces behind weather, you know, the ocean is a big part of that. And then, you know, this climate destabilization and stuff like that, that is exacerbated by our excess energy consumption and burning of these fuels, is creating more scarcity in natural resources and food and clean drinking water. So it's sort of a self-perpetuating cycle. And, you know, that's stuff that we have to think about when we're designing our buildings. You know, we don't want to just ignore all this stuff and think, well, I'm just one person, you know, what I do doesn't have that big of an impact. Well, you know, when there's a world full of 7 billion people and everybody's thinking the same way, it adds up pretty quickly. So here is a chart of energy flow in the US. On the left, we have things that are considered primary energy. These are energies found in their unaltered state. Electricity is not a primary energy. Typically, we have to burn things and make stuff spin to create electricity, right? So we've got solar and nuclear and hydro and wind, geothermal, natural gas is a primary energy. We still have to extract it from the ground and process it. And then coal, you know, all this stuff takes processing, stuff like that. You know, all this stuff are ways that we create electricity to power our environment and our daily lives. In the US, buildings consume over 70% of our electricity and 40% of our energy. If you look at this chart, draw this thing. Let's see. So like, no, that's not it. There we go. You know, roughly 2/3 of our electricity generation here is going to rejected energy. You know, like coal, for instance, is sort of dying out. Some of these coal-fired power plants are becoming used less because natural gas is a more cost-effective and it's more efficient. Coal is limited in how much energy it can produce because it's only about 30% efficient. So this means you have to burn 3 units of coal, get 1 unit of energy that will go to the building, which also has waste. So we can see that, you know, this waste on the backside of this, that's, you know, there are efficiencies for all of this stuff and limits on the efficiency. And that's what we're trying to think about, is efficiency in our built environment. And we can design that into our buildings so we can, you know, sort of make these smaller. When we build efficiency into this stuff and can cut down on some of this rejected energy, it then in turn, you know, affects the back end where our buildings are and the energy that's wasted at our buildings, and then it affects the front end on our energy generation. We have to generate. We use less electricity if we can make our buildings more energy efficient. But you know, you can see some of these flows and how complicated it is. And so, like I said, when we eliminate waste on the back end, you know, we can eliminate some of the need for some of that generation. That's an important thing to remember. So sort of the way that we're going to stay up there. Sorry. So some of the things that allow us to build energy efficiency into our buildings are standards, codes, and certifications, right? So professional organizations make standards, right? We've talked about ASHRAE, AIA helps with that stuff. There's a number of organizations, USGBC, you know, we know about LEED and all of that stuff. So we've got organizations make standards, okay? So these two things are what are going on right here. These two things are closely related. And then organizations like the ICC, the International Code Council, sorry, I'm gonna get something that I can write with and not have to write with my mouse because this is sort of painful. So the ICC, people like them rely on these standards to make model building code, what we think is like of what we think of a high performance building when we think of this stuff. So ASHRAE and some of these organizations are coming up with stuff that we need to do to make the most high performance building that we can have, right? So, you know, that's not always what gets put into building codes. Remember that building codes are basically the worst building you can make. Like if you look at the NC building code, they're a minimum threshold for building performance. They're the worst building you can make and still be safe and adhere to these standards that people are setting forth. But the ICC and these organizations work closely together. The ICC makes model building codes, and then the state building codes sort of model what they have off of the ICC and, you know, put their own spin on it based on, you know, where they are, climate and, you know, economy and stuff like that. So, oops, sorry. So, you know, building codes exist for, like I said, yeah, worst you can build. And then, you know, building codes exist for safety, right? And so that owners are assured that they're getting what they pay for, that they're not being cheated in a way by contractors who aren't sticking with these codes and standards and stuff like that. And in turn, this sort of, there are certification programs and targets that we shoot for. People like ASHRAE and all these others are coming out with these certification programs for early adopters. Like LEED is one of these programs where, you know, there are financial incentives and there are marketing incentives and stuff like that. It makes your company look better if you have a building that is LEED silver or LEED gold or LEED platinum or whatever. People are using this sort of as marketing, but at the same time, there are people out there who conduct themselves. Maybe you guys have heard of B corporations. B corporations are really cool. You should look into that. It's a certification for companies that says that they conduct themselves in a way that looks at energy use and stuff like that. But the point is, there are people out there that care about energy, that care about the environment, that care about energy efficiency and stuff like that. And there's some of these early adopters that are going to be pursuing these certifications and programs and stuff like that. So that's driving stuff on, you know, on the front end, driving us forward as far as building energy efficiency and the best buildings that we can build and stuff like that. And it pulls this along with it. So as our knowledge and technologies improve, and we get, you know, these super high performance buildings, it's sort of dragging the code along with it and raising that standard as we go along. And especially as more and more people start to pay attention to climate change, climate destabilization, stuff like that, and the need for this stuff. So, you know, this is sort of what we're doing. And, you know, this stuff happens slowly. The code changes. In North Carolina, we're on a 6-year cycle. So this stuff doesn't happen overnight. You know, technology in the built environment changes slowly. Stuff doesn't just happen overnight. So moving on. So sort of how, little bit of background on sort of how we got here. There we go. So back in the 70s, we had the oil embargo where OPEC basically cut our oil supply off, and people started to realize, hey, there's a finite amount of oil, or oil and energy resources are limited. We're really dependent on this stuff. And when these countries that have control of our energy resources cut us off, it's a bad deal, right? So it sort of sparked this movement to where the EPA was created in the 70s, and we started trying to increase energy efficiency in the built environment. So we started making our buildings tighter, but that led to moisture problems because when you think back to the building as a system and you think back to that grandma's house video, when you change one thing, it has sort of a domino effect and changes a lot of other things that maybe were unanticipated. So we started building our buildings tighter. We started to develop moisture problems and something called sick building syndrome. All those pollutants and stuff, and the things that we talked about regarding indoor air quality came into play. People weren't ventilating their buildings, and people started getting sick. And so there was this sort of pushback against energy efficiency and building tighter buildings because they didn't know everything that was at play at the time. And people were saying, no, we need to keep our buildings loose because you get sick. And, finally we're starting to figure it out. So we started ventilating better. We started having better control of our thermal moisture and heat. We come up with things like ASHRAE 62.1 for ventilation. And we started to realize that we need to think about these buildings as a system rather than thinking about each of these things one at a time. We've got all these certifications and programs to help us improve certifications. The best ones at present are Passive House and Living Building Challenge. There are other standards like the Well Building Standard. There's a link here at the bottom of the page that you can check out, the Well Building Standard. But with Energy Star, you can have ratings for the appliances in your home, and you can have an Energy Star certified home. And there are, that's stuff that the government's doing. There are certifications for, like I've said before, multifamily structures that are sort of related to Energy Star. And portfolio manager is one thing where if you have a multifamily structure that performs at a certain level, you can get a reduction on your insurance premium on the loan for your multifamily development. But there's all sorts of stuff out there trying to push people along and trying to increase energy efficiency in the built environment. So some of the priorities for low energy commercial buildings: window to wall ratio. So like I said before, the windows are our weak point in our building envelope, right? They're not as well insulated as like a 2x6 wall with bad insulation in it or something like that. So we don't want to just put windows all over our building, right? We're going to be losing heat. There's going to be air leaking through them, stuff like that. So there's a sweet spot right in that 30 to 40% range for how much of your facade is made up of windows. So we want to increase our window performance. Low U value, so having high insulatory properties and carefully selected solar heat gain coefficient, which determines how much of the sun's radiation comes in. So if you have, some of you who have taken solar and stuff like that know that when you're in the northern hemisphere, the sun is lower in the sky towards the south, so you orient your panels towards the sun, right? So you have a southern orientation on your panels. Same thing with a building. If you want to have a passive building design and utilize some of the sun's energy coming in, you're going to have higher amounts of glazing on your southern facade to try to capture some of that sunlight coming in the winter. And then, in the summer, you're going to have appropriately sized overhangs to block the sun out, to keep some of that solar heat gain out when you're trying to cool your building. So we want to increase wall and roof insulation, obviously. There's a point of diminishing returns with that. And there have been studies on that to where when you hit that point, then it's time to start investing in renewable energy, stuff like PV, typically is what you'll see on small residential stuff. And so we want to also separate ventilation air from HVAC. If you have a room that doesn't have that many people in it, there's not that many people producing carbon dioxide, and the air might be okay in that room to keep recycling through the system to keep it at the right temperature and humidity. But then when you start running out of fresh air, then you want to introduce the ventilation. So when you have some of these units on campus, some of these buildings on campus that have 100% outdoor air, you're constantly having to condition and dehumidify air, and then you're spitting that already conditioned air out when you introduce more ventilation air. So we want to try to hold on to some of that air that we condition, and as long as we can, as long as people are still comfortable and happy inside. And so another thing is the use of occupancy and daylighting controls and equipment. We don't want to have a bunch of rooms on campus that are unoccupied that have the lights on in them, right? So we put daylighting controls in there and equipment, so it only turns on when we need it. Otherwise, you're just wasting energy. We want to reduce the equipment, plug, and lighting power densities. So you can have 2 light bulbs that use the same amount of energy, but one of those bulbs produces more light. So we want to start looking at the light fixtures that we spec on our designs, start looking at CFLs and LEDs and stuff like that. We want to use demand controlled ventilation. Again, people produce CO2. When there's plenty of fresh air in a room, you don't need to recycle that air with fresh ventilation air. And there are sensors in some of these more complex HVAC systems that will measure the amount of CO2 that's in the air and then introduce ventilation air when it gets above the limit where we want it set. We want to improve HVAC efficiency and use heat recovery. So when we do exhaust the air, when we need ventilation air, we need more fresh air coming in, we've already paid to condition the air that's in that building. There are methods that we can use to run that air through a heat exchanger when we're bringing fresh air in, and bring the fresh air in through a heat exchanger as the exhaust air goes out, and the exhaust air will transfer some of that heat or that you put into it already, or if it's cold air, it will pick up some of the heat that's coming in and take it out with it. So it cools down. If you're trying to cool, it will get rid of some of the heat that's in the air as it comes in, that fresh air. So we want to use variable speed controls on large pumps and fans. So when you size a system, it's sized for sort of worst case scenario, right? That's not always the most frequent operating conditions that it's going to be under. So we have these things called variable speed controls. There are variable frequency drives that supply motors with a certain amount of electricity, and you can vary the frequency of that electricity, and you can scale up or scale down the peak, sort of the peak operating performance, or the range at which the peak operating performance is found. You can adjust the speed of that motor accordingly based on the loads and the conditions that it's operating under. So we want to have also a simple and compact building form oriented to the sun. So again, pay attention where your southern facade's facing. Use some of that free energy from the sun if you can. And then, on the other sides of your building, if you have a ton of glazing on the northern facade in the winter and you're not getting any energy, you're putting that glazing there. It's the weak point. So you're going to be losing energy through that glazing. So, you want to pay attention which way your building's facing, which facade has the most glazing on it, and then pay attention to the ones that are not going to be getting the sun's energy and adjust accordingly. So we've talked about some of these ASHRAE standards, 90.1 and 90.2. We remember that these are about energy efficiency. Another one of your quiz questions: list parameters in key sections of the standards. Discuss how to interpret envelope tables in 90.2. So in adhering to these standards, there's two paths for compliance. There's a prescriptive path and there's a performance path. These two, there's 90.1 and 90.2. These are differentiated because 90.1 is everything except low-rise residential buildings. You see in this graphic up here, everything except low-rise residential buildings, and then 90.2 is residential. So residential buildings and commercial buildings have different uses, right? They're going to have different occupancy schedules when we're under normal circumstances. If you think about it right now, think about all the buildings that we were having class in on campus and the amount of time that we spend in those buildings, the loads and stuff that those buildings are being exposed to, I guess, when you're trying to condition a building. When it's hot or cold outside, you're putting energy into that building and you're trying to keep the people inside of it comfortable. Well, now it's reversed. We're all at home. So our occupancy schedules and our water use schedules and stuff like that are reversed. So you're at home all the time. You know, you're probably using your bathroom more. You're using more of your materials at home. You're using more energy at home. Typically, you know, we differentiate these two things because they're so different. They're like night and day. You know, during the day, you're in a commercial environment and you're using all the energy in you're in the commercial domain, and then at night you go home, and that's what determines your schedules and the amount of energy you use. So we need to differentiate between these two things and set sort of different standards that apply to each one. So again, there's a prescriptive path and a performance path. The prescriptive path is, you know, you look at these check boxes, like you need, for instance, R value of 30 in your walls. So you design your walls with an R value of 30, you check that box off. Window U factor of 0.3, you can check that box off. If you want to build something that's more high performance, or you want to deviate from some of these listed specifications, then you're going to follow the performance path. If you can't meet the prescriptive path, or you want to deviate from some of that stuff, you need to create an energy model of your building with a baseline, with all of your values meeting the prescriptive path, and then make your alterations in that energy model and show how the design alterations that you want to make and improve the energy performance of your building. So, you know, for instance, that if you want to have higher glazing on your southern facade and you're outside of that 30 to 40% range, you can put, you know, more glazing on the facade in your building and show that you can utilize some of that energy from the sun and reduce your heating load in the winter. Again, that was one of your quiz questions, or prescriptive path and performance path. So major factors of 90.1, envelope is important regardless of what sector you're in, whether it's residential or commercial. The commercial sector is going to be subject to, again, different occupancy schedules, but also different heating and cooling loads. If you look at buildings like the library and the number of computers that are in the library and the lights that are on in the library, all that stuff's producing heat. So you have different cooling loads, and so it's going to affect your HVAC schedules. Even in the winter, the library spends most of its energy cooling and trying to get rid of excess heat that's in the building. So that's something to think about. So when you have all of that extra heat production in a commercial building because of these loads, the envelope is not going to matter quite as much as it does in residential, where you don't have all that excess heat generation in your home. And so the envelope is going to make more of a difference in your house than it's going to in commercial buildings. But we always want to, you know, produce as good of an envelope as we can, because otherwise you're potentially going to be using more energy than you need to. 90.1 provides systems efficiencies for HVAC systems. There are tables of efficiencies in 90.1, and manufacturers are aware of this stuff and they try to meet these efficiencies. It's going to be hard, or it's not going to be hard to find stuff that meets these efficiencies when you're speccing your HVAC equipment and other equipment in your building. Manufacturers are aware of this stuff. and they shoot to try to at least be in line with these efficiencies, if not better. Your service water heating is another important place to limit energy. You know, in your house, most of you probably have a water heater that is not on demand, meaning that you have a big tank of water that you're heating all the time. You're keeping it within a temperature range, right? So when you're not at home, that temperature is, and the water in your tank is at that temperature range. You're keeping that stuff hot all the time, so you have hot water available for use. So think about that. You know, if you guys are not taking super hot showers and turning the water all the way on hot, and you're not running out of hot water, turn your water heater down. You might save yourself some money on your electricity bill. But you know, that's another big place where we can design in more efficiencies and better systems to save ourselves some money and some energy. Power systems are another big thing that we need to be aware of. Being able to monitor how energy is used in your building in different parts of the electrical system. For instance, on campus, they have all the HVAC systems are being monitored, so they can see when an HVAC system isn't working properly, when it's using too much energy, and say, oh, well, something on this part of this system, this building probably needs to be replaced. If you can't monitor your systems and you're just looking at a bulk energy use, you don't know if you're using too much energy or not. Really, it's much harder to have a firm grasp on whether or not you're wasting energy somewhere if you can't split up your energy uses. Lighting power densities, again, we talked about that stuff. This is measured in watts per square foot of floor area. You can have two lights that use the same amount of energy but produce different amounts of light. And you know, if you guys have taken architecture, you can design in you know, natural light and stuff like that to try to reduce some of these loads, like on your lighting. This is a table of climate zones and sort of associated U values with that climate zone. So maybe you guys haven't heard of a climate zone. We'll talk about this more later in the class. So for code, we split areas into zones based on the weather in that zone, right? So in some parts of North Carolina, it's not quite as cold as it is here. So your code values are going to be different. You're not going to need as much insulation. Your heating system's not going to be as big as it is here. You know, here we don't have that as much of a need for air conditioning. So all this stuff is taken into consideration, and there are regions that are split into larger areas where the weather is similar in all of those areas. I think in North Carolina we have 3, 4, and 5. So these U values, U value is the inverse of R value. Probably most of you have heard of both of those things, or at least R value. U value is 1 over the R value. R value is 1 over the U value. So in R value, it's better to have a higher number. That means you have more resistance to heat transfer across that material. And with the U factor, the smaller the U factor, the better resistance to heat transfer across that material. Again, U value and R value are inverse of one another, and we'll see more on that later in the class. So another thing that a lot of this stuff sort of defers to is safety, right? So a big concern that we have in the built environment is fire safety. So we want to know what NFPA stands for. We want to discuss the purpose of NFPA 285 and explain how low energy buildings might create fire challenges. So again, like I said, this in some ways supersedes all the other stuff that we talk about. NFPA 285, Standard Fire Test Method for Evaluation of Fire Propagation Characteristics of Exterior Wall Assemblies Containing Combustible Components. So we build our houses out of stuff that burns. You know, most of the stuff that's in residential will burn. There are fire retardant things that, you know, we've come up with, but a lot of this stuff will burn. There have been examples in the past where for instance, exterior insulation has made fires worse. So we have to keep a close eye on this stuff. When styrofoam melts, if you don't put brakes, and if you look at this picture down here, it sort of shows some of these brakes that they have in the insulation. When this stuff melts and it's on the exterior of your building, or even if it catches on fire and there's no brakes in this stuff, it acts as a channel or conduit for fire, or it can, you know, act like a chimney and melt and draft and pull hot air up, and the fire will go along with it. So there are companies that build these and test them. They'll build a wall assembly when they're you know, experimenting with new materials and stuff like that. They build wall assemblies with windows in them. That is the big issue, is having a window and where the fire can spread. So they'll build these wall assemblies and burn them for 30 minutes or something like that, and watch the fire as it spreads and analyze it and determine whether or not it's safe. Sometimes, you know, like I said, putting these fire breaks in can help stop the fire. And again, you know, foam can serve as a conduit for the fire and really cause it to spread really quickly. I don't know if you guys remember, back in, I think 2018, there was an apartment fire in a building in London or somewhere in the UK that I think had some of these issues, and a lot of people were hurt. I think some people died. But you know, the takeaway from this is, as we make buildings more energy efficient, we have to look at the materials that we're using. We have to think about the building as a system, look at all of these, the methods that we're using, the materials that we're using, and decide whether it's safe or not, and whether there's any risk that we're adding and trying to make our buildings more energy efficient. Quantitative problem solving steps. So it's good to have sort of a formalized problem solving process that we can go through when we're given different scenarios. You know, in your classes, you're given these stylized problems that are sort of cut and dry in a way, and it's definitely not always going to be like that when you enter the workforce. You're going to be looking at you know, lots of different variables, and you're going to have to try to pinpoint what it is your problem is, and then see what the solution looks like before you can, you know, lay out the steps where you go from defining your problem to finding your solution. So, you know, today we're going to define a set of steps for quantitative problem solving, and then we're going to apply those steps to some problems. We'll see how far we can get. I don't want to get too far and not make it that far in other classes. So here are some graphics on problem solving that were taken from the internet. These illustrate steps in a variety of problem solving processes. You can see some of them use the term design in them. So when we think about building design, what is building design? It's sort of like a problem. An owner is going to come with a set of things they want to address, or uses that they will have that they need in the building. They'll come to you with, you know, some ideas, some solutions that already exist for these said problems, and then you'll probably be presented with some less cut and dry stuff, some more some issues that will require some creative thinking. And you define your problem. You look at what the outcome is going to look like, or what you think it will look like, and then you go through some of these problem-solving processes, or whatever, you know, works for you as far as what you come up with, and then you try to come to a solution. So, you know, building design is a problem-solving process, just like mathematical equations are. So first, you know, in a lot of these, they say, define the problem. Obviously, step one is define the problem. You have to know what your problem is before you can solve your problem. And then, like I said, get an idea of what the solution is going to look like. And then you can lay out your steps towards that solution. So in terms of this class, what is our solution going to look like when we have a problem? You know, whether it's something we're trying to figure out in a design, or whether it's, you know, mathematical in terms of some of the math problems we'll be looking at. You know, our solution is going to have certain units. So figure out what units you think your solution is going to have. And from there, you can build a strategy on top of what you already know. And you will gather information and organize it. So, you know, define this on the top right, define, collect, brainstorm, or define, brainstorm, pick a solution. You know, you're going to come up with a strategy that you think is going to work, and then try to apply it. And this is going to be an iterative process for a lot of things you do in your life, whether it's coming up with a design solution for a building, or, you know, trying to solve a mathematical equation. It's not always going to work the first time. Sometimes it's going to require multiple tries before you get it right. So then you're going to implement your strategy. You try the process and determine if you have answered your question, if you found the solution that you were looking for. What does your process result in, and how does that compare to what you thought your answer was going to be? And like I said, iterative process, not always going to work the first time. Don't get discouraged. If you try something and it doesn't work out the way you had hoped it was going to, try again. You know, and that's anything that you're doing, whether, you know, trying to learn new stuff about building design, or, you know, trying to figure out sort of what path your career is going to take. You know, this stuff is just it's all a learning process. Don't get discouraged if things don't work out the way you think they're going to, or you had hoped they are going to. Try again. So one process to consider. So like I said, the first step, we're going to identify what the answer will look like. A good way to do this in terms of this class and some of the problems that we're going to be looking at is put it into words. A lot of the time you might not have, you know, the problems you're going to see are going to be put into words already. Reword it. And if it still makes sense to you and you can put it into words, then you probably have a relatively firm grasp, if not a really firm grasp, of what the problem is. And again, then identify what units you want that answer to be in. Step 2, we're going to classify the type of problem. Is this a conductive heat flow problem? Is this an electrical energy consumption problem? That's going to help us orient ourselves with the problem and determine what some of the following steps are going to be. So we identify and organize what is given. We look at the variables that we have, we organize them, and we see, you know, what variables are there that we need, what variables are there that are you know, irrelevant. And that's something that's going to be good to get a hold on as you transfer into a normal working environment. You know, not everything's going to come into play on every problem that you have, and you have to be able to eliminate the factors that you don't need from the ones that you do need. You will often have to look stuff up and be resourceful. That's something that, you know, I'd like to stress, being resourceful. Like I said, we have all the information in the world at our fingertips all the time. Use it. And so you can find, you know, anything that you need for this class or anything in life in general. You can find something on it online, and you can learn anything that you need to learn off of YouTube. You just don't get a piece of paper for it saying. So again, strategize how to manipulate what is given to eventually find a solution in the units listed in step 1. So again, it's an iterative process. If you have, you know, a list of variables that you're given, and you look at the units that they have, look at the units in the answer you think you're going to have, and try to work your way through that so that you come up with the units that you want in your answer. Implement your strategy, see if it works. Evaluate the answer to see if it makes sense, and revisit previous steps if needed. If you didn't get the units that you came up with initially, if you're certain on those units, you know, then you either took a misstep somewhere or you left a step out, which is often the case. Sometimes there's an additional thing that we need to throw in there, an additional conversion to get where we want to be. So, step one, the problem is to find, say we haven't, and we're looking for energy. What is our energy going to be? It's going to be in units of BTU or watts or something, watt hours. I would classify this problem as, for instance, a conductive seasonal energy. So organize what you know and what you have to look up. Say we're given 1,000 square feet as our area. We have an R value of 20. Remember, resistance, higher R value is the better insulatory properties, and it's in Boone. So to find the answer to this solution, to this problem, we're going to have to look up heating degree days. I know you don't know what heating degree days probably are, but we'll go over that more. And so we're going to say that we have 4,800 heating degree days for Boone. This is made up. I did not look it up. There's a lot of variables that come into play. So we have, what equation do we need? We need energy, and we have area, we have R value, we have heating degree days, and times 24 hours a day. So step 4 to 5, document the order of the equations that you will use to try to solve the problem. When you put this stuff into practice, this is what it's going to look like. So you've got area over R value times the heating degree days times 24 hours a day. And so we're going to have 1,000 over 20 times 4,800 times 24 hours a day. Does this answer make sense? Often when we're doing calculations like this for energy use and conductive seasonal energy, stuff like that, often the answers are in the millions of BTUs. This is just an example. But if you have, say you're trying to design a wall that's a high performance wall. So code for a wall in Boone is R19 in simplest terms, and you're trying to design a high performance wall and say you're shooting for R40 or something like that. That's going to be somewhere along the lines of a high performance wall in Boone. It's going to be well above R19. You come up with a design that results in an R value of 10. Somewhere you went wrong. Have an idea of what the outcomes should look like, the realm that it's going to be in, and that way you can know that if you come up with something weird, I did something weird somewhere. So we're going to try to solve this problem. We'll get into breakout rooms, work together for a little bit, and see if we can come up with an answer for this problem. So if you have a 4,500 watt electric resistance heater, the water heater leaks, making the heater run for 10 hours a day. How much will this cost me on my electric bill? And just so I don't show you the answer, I'm going to pause my share just in case. Well, we're not going to get into breakout rooms just yet. Hang on. So here's what this problem looks like when we work through it, okay? So the problem is to find utility costs. So in what terms does that make sense? When you get your electricity bill at the end of the month, you get dollars per month, right? So this problem will be classified as energy and cost. So we're going to organize what you know and must look up. The known, we have a 4,500 watt water heater, and it runs for 10 hours a day. We need to come up with a cost that's per month. So we're going to convert hours per day into a month. There's 30 days in a month, 10 hours a day. So we're going to multiply times 30. Electricity costs, we need to know what our electricity cost is. So somewhere in the ballpark of 10 cents per kilowatt hour, something like that. There's not really a set equation for this. It's just, you're just converting units essentially. So we're going to document the order of the equations that we use and try to solve the problem. We want to convert power to energy per day. So we'll take power and multiply it by time. And then we want total energy per month. And then from there, we can go cost of energy. So, when you come up with this, when you write this out, you get about $135 a month. Work this out and see if that's what you come up with. Take a couple minutes, see if you come up with the same answer. Maybe I did it wrong, hope not. Write it out, see if you can figure it out. Take just a few minutes. And if you're somewhere that you can't write anything down or you don't have writing materials, then just sit tight. I'll give you 5 minutes, see if you come up with the same answer, then we'll talk about it. What'd you guys come up with? Were you able to arrive at this same answer that I got? 135 bucks, makes sense? Okay, so what did we have to do? Well, look, if you didn't come up with this answer, this is what I did. So you've got 4,500 watt heater, right? We put it over one, and we're going to start talking about dimensional analysis. So when we look at units, if you, in this idea of dimensional analysis, we treat, and you guys can Google this and start thinking about it, but in dimensional analysis, we can treat our units as algebraic variables, right? So when you want to convert some unit, you have to multiply it by a conversion factor, right? So typically that's you're going to have your unit that you have on the top, your starting unit, and then you multiply it by your conversion factor. It's going to be 1 over something. So it's going to be 1 over your starting unit, or something over 1. So we've got 4,500 watts, and you can look more into dimensional analysis. Google it. We can talk about it later. So 4,500 watts times 10 hours a day. We want to convert days to months. So we have 10 hours a day times 30 days per month. Day is going to cancel. And so then you have hours per month. So you're going to have to get that to cancel too. So we have 4,500 watts. Our energy bill is in kilowatt hours. So we have to convert watts to kilowatt hours. So we multiply times 1 kilowatt, or where is it? I think I did that wrong. Maybe no, there it is. So times 1 kilowatt over 1,000 watts. So your watts cancels. And then we want to cancel kilowatts and be left with just money. And we need to cancel hours too. Hours, 10 hours per day, and 10 tenths over kilowatt hours. The hours cancels. And then we're left with just 10 cents times all that other stuff. Come up with $135. I know that was sort of rough, and it's hard when I'm not writing on this stuff. I'm going to try to get something to write on this stuff. But anyway, we all came up with the same thing. So unit conversions, learning objectives and unit conversions. Understand what units are important in this class, apply unit conversions. So it's important to be able to manipulate units in this class as we work through some of these problems. And that was what I was talking about with this dimensional analysis. There's different terms for techniques for doing this. Dimensional analysis is just one of them. And there are some videos online that you can look at. And then we're going to talk about the train track method as well, which is sort of what we just looked at, but it'll make more sense in later slides. There's a lot of things to consider. So this is a conversion sheet that's out of an engineering study book for getting your PE for becoming a licensed professional engineer. This shows us how to convert between a lot of different units that we're going to be using in this class. And you can always go online and Google conversions and use automatic conversion calculators. That's fine. Obviously, you're at home and all of this stuff is open book. So, but check it. Be sure that you check it and make sure that it makes sense. And be deliberate in the units. You got to pay attention to the units you're putting in, the units you want out. Sometimes there are units that will look the same as other units, like specific heat capacity and heat capacity, for example. One of them is energy per degrees per some unit of mass, and then the other one is just energy per degrees. So pay attention to that stuff when you're using these automatic calculators. But otherwise, it's fine that you do that stuff. So units are tricky. Why are units tricky? So when it comes back to energy in buildings and this stuff, as as does almost everything that we deal with, it boils down to money, right? So we're paying for energy, we're paying for these systems when we put them into our buildings, and it can add up really quickly if we're not careful in our calculations. We make mistakes. We can end up costing somebody a lot of money. So, you know, different sources of energy are metered or tracked using different units. Electricity's metered in kilowatt hours. Natural gas is in cubic feet, which in turn goes to therms. So the therm is 100,000 BTUs. So, you know, that's something that we have to be aware of, is the different units that we're using, the different ways that we track different energies. And, you know, you can convert one to the other. And so, let's see where I'm at. Electricity is tracked using kilowatt hours. This is total energy consumption. You might also have a peak demand charge, which is peak power flow for a 15-minute period, which will be kilowatts. These charges can be pretty substantial. So when, like, if you're a big commercial facility and you have really big equipment that's going to be running, the power company has to be able to meet your demand. If they're not meeting your demand and a big piece of equipment kicks on, it can drain sort of the power flow, and you can have whatever the opposite of a power surge is, I guess. And you know, it can drain the power flow to other people that are on that same system. So the electricity company will charge you. If you have really big equipment, they'll charge you that peak demand charge. And again, natural gas is tracked using cubic feet. Gas is a consistent energy density. So when you combust a certain volume of natural gas, it's consistent. You get a consistent amount of energy output. And again, sometimes natural gas is tracked using therms. A therm is 100,000 BTUs. So sometimes we'll want to do stuff like this example here at the bottom of the page to see how much energy you're going to be producing and how much energy you're going to be using, and see how much PV energy you're going to need to be net zero. So look at the slides. We'll stop right there for the day. I think we'll pick back up right here